So today I'm going to go through the other language extensions, but I'm worried that the last video was extensively boring. And so I think this week what I'm going to do is I'm going to try and actually make something quite fun and intricate with you instead to go through them. So I've just created a new Haskell project with Cabal, and let's get inside it. I've made no changes yet. Come on. There we go. And what I thought would be interesting to do is to sort of make a servant style, and I'll go over what that means, a servant style sort of remote call protocol thing, remote procedure call, RPC, that's strongly typed. So servant, by the way, is this amazing library where you can do things like you can say, my API is get user and then capture int ID. I think that's the way it goes round, and that's a get request, which is JSON. I can't remember how it's all done. JSON and then user or something. You can write something like that, and what that refers to is first of all a URL, which is /get/user/ and then some number, some ID, and then it's a GET request that returns a JSON representation of a user. And when you implement this in Haskell, to write the server, you simply have to write the function get user, doesn't matter what you call it, type int to I think it's handle user. I think that's the type you have to describe, and that's just a normal model monad. I can't remember if it's LE or EL. And to write the client, you write absolutely no body. You just get given for free this get user function, which is of type int to, well, it's exactly the same, but it's client user that you can just use. You don't have to even give that a body. So it's amazing. You can generate these strongly typed REST web interfaces from just a type. But I mean, it's a weird type, isn't it? I mean, this infix that I was just about to delete, that's a weird type. What does it mean? You know, types normally have this concrete meaning, like an integer is an integer. What did that mean? And today I'm hoping to sort of implement something relatively simple that's a bit like that. I don't know how simple we're going to be able to make it, so I'm probably going to have to split this up into parts. So I thought first, let's just get going and let's look at defining those weird types. So the weirdity that I showed you was this infix type. And we can, in Haskell, just define infix types. There is a catch. But this is what we're writing. Infix R9. Okay, so I've done something. I've defined a data definition. I've not got an equal sign or a where clause. Very strange. I've got bizarre notations around the types that are inputs. Remember, this is this side of the equal sign. So A is a type, but I'm saying this type is of type K, or even weirder, this type is of type star. And I can guarantee you that when I close this Vim session, it will error. Yep. But it errors in a useful way. It tells me that I need kind signatures or poly kinds or stuff like that. So what I'm going to do is I'm going to add some language extensions to get these errors to go away. So the one I'm going to add is poly kinds. I'm also going to add type operators, and that's going to allow us to have these infixes. So polykinds allows us to do this magic, and type operators allows us to have this infix symbolic type constructor. So let's have a look. I've successfully managed to make all those bad things go away. So let's look at this. What am I saying here? Well, these are kinds, and kinds can be thought of in Haskell as sort of the types of types. So let me just write down some normal Haskell types. Now, all of these are of type star, because star just means type. I think you can now write type. I'm not 100% sure, but star. Those are all of sort of type star, and we say that's their kind. The kind of those types is type. We say it type. Now, what's interesting is if I start to remove parts of this. So if I go and I replace this, oh, that's not how you do that. No, that's not how you do that either. Control R? No. Oh, I know why. There we go. If I remove that, what happens? Well, this becomes of type star to star. And if I go and remove that, this becomes type star to star to star. Because either I have to give it 2 types, and I get a type. If I give it 1 type, then I still have a type-to-type thing. So it's just like types, but for types. And that's why we call them kinds, or as we say types so many times that everybody gets confused. Great. Okay, so what have we specified up here? We've specified that A is of any kind, and we've specified that B is concretely a type. Good. I hope that made some sense. There was another weird thing that we did. Oh no, we didn't do it. So we can in servant, we can write, we could say that we have this configuration API, but we also have this control API. We have this sort of OR type in the middle. And then I can say that type config API equals set blah, 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 blah. And I can also say that also in this API we have, oh, disgusting, there we go, get or something, which gets some configuration, and that is blah, 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 blah. So there's this kind of combinator that allows us to join APIs together. Now let's define that one. That one's got a, in some respects, easier and in some respects harder type. So luckily we don't have to deal with kinds. But we do have a completely nonsensical middle bit implementation side. So what's going on here is we have, and I think this will build just fine. Yep. We have just a normal infix, just like the top. We've not had to specify the kinds. And then we have exactly the same thing on the other side. It seems so meaningless. There's nothing complicated going on. I have a type constructor, just like maybe is a type constructor. I have a constructor, just like just is a constructor that takes 2 arguments. It starts with a colon, which is what allows us to make it this infix. This side, at least, is vanilla Haskell. I could remove type operators and polykines, and if I made this not infix, this would still be valid. You can make infix constructors in Haskell with a colon at the beginning to say that they're, just like they normally have capital letters. You can also have a colon for an infix. It seems all meaningless, this one, but that's because what gives these libraries power, what gives them functionality, is their type classes. But I'm going to give it an infix precedence at least. Lovely. I don't know if I've gone over this, but when you define an infix, you can give it a precedence. So the reason why we want this to be weaker than this, hence we give this a lower number than this, and we're saying it's right associative. Good. What else did we have? We had a capture. So capture, we have that. That is our type for capture. I think when I did it before, I had also some string, but we're going to ignore that for now. And then because our remote procedure call library won't have any. We're just going to start writing that now. We're not going to look too hard at servant in this tutorial. And we might have a result for our remote procedure call. So result is going to be, again, just a type. So already this is bizarre Haskell that we've not seen before. But it is quite simple. We're just defining types, nothing more. This type is very easy to get your head around. It just seems pointless. This one harder. These ones we're just specifying that A has to be sensible, if you like. Has to be just a star. Good, and I think that'll build. And what we want in the end is we want a type class. We want 2 type classes. So we want to make some classes. And we want the first one to be has proc, say. We give it an API. And the second one, do we want to... Yeah, we're going to want some kind of routing function, I think. Anyway, we're going to call it has server, say. And so I'm going to change this to client. So the client is going to request a remote procedure call from a server. That's how this is going to work. Just like a REST API, but it's going to be based on binary protocols as opposed to HTTP requests. So client is quite simple in what we want it to achieve. We want to have this client function, and its type is going to be something along the lines of client. Proxy, which I'll show you what that means in a sec. API to client API. So I'm giving nothing away. I haven't told you what either of these things are. So client API, I'm going to change to IO for now. It's just a monad, but we might want a client monad later. Proxy API. So proxy is a weird type. It's in standard Haskell, data.proxy, and its type is this. So we have this sort of ghost type parameter here that doesn't appear in the implementation, and it just allows us to get type stuff into the type of a function without having it in the implementation of our function. And that's really useful for a lot of these, because if you look, they don't have an implementation. They are just type data. So proxy really allows us to use that data well. And so I'm also going to introduce another language extension, and that is I can write things like this, which means that. And that's really useful. It saves a lot of space. And that language extension is type applications, I think. We're also going to want scoped type variables. Now that means, you'll see, I'll point it out when we get there. So good. Another thing we're going to want, which is a bit strange. Oh no. Change of plan. I am going to put client here. Oh, so annoying. I hate it when I make mistakes like that. Okay. We're going to add this new idea. We're going to add a type to our type class. And for this, we're going to need type families. So what this allows us to do is this allows us to define a type in every instance, and you'll see this used a lot. So in our server, what functions are going to need? Well, we're going to want this serve function, I guess, or a root function. Let's go for root. and we're going to have this Proxy API again. We're then going to have this server API, not giving anything away. And then we're going to have a list of strings. That's going to be our input. So we're going to split everything up in our string input on that, basically, you'll see. I might change that later. And we're going to return maybe IO string, because that's what we're going to send back to the client, if anything at all. Good. Okay, so have we done anything illegal here? Yes, I've not defined server. So server. Yes. How am I going to go about this? I think we're going to do it exactly the same. So type server. Yes. I know what I'm doing. I promise. Okay, good. Lovely. I'm going to hesitate a lot in this tutorial because this is quite tricky stuff, especially when you don't really have a plan. So let's start adding instances, because this is not going to make any sense until I add instances. And even then, it might take a while for it to sink in. But okay, let's go and do that. So, instance has client of, we'll do the easy one to start with. So I'm going to say has client A, has client B, and we're going to define has client A, B. Where? So on the assumption that A and B are a member of this instance, how do I define that has client of that is, an instance? The way we're going to do that is we're going to say, well, let's first define our type. So what type family allows us to do is define a unique type based on all the other types that we can use. So I'm saying here that the return type of this function is given by type, which has a parameter API and is a type. You'll see what I mean. So client, and then it's going to be that's not right. B equals. So you see I'm defining a type here. So just like I said, it takes in something of API, which is here. And the output is a type, a fully applied type. So the type of this is client A, client B. And then client itself is going to be, so we're going to ignore its input. That's what we're going to do, the first input, because it's a type proxy, and we don't ever use proxy. We always ignore the input. It's just to make the type stuff work out just fine. And that's our only input. So what we're going to say is we're going to say it's equal to client proxy at A, client proxy at B. And that should, yeah, that's okay. So what I've essentially done is we can have a function. Let's look at this client function actually. So if I have something of type, I'll say x, y, and I call client on it. Client, and it would be proxy. So if I call this function, we essentially have a bunch of rewrite rules here. So what then happens is Haskell goes, okay, so that is the same. as client of X, client of Y. Now, this might look a bit confusing, but remember that this here is this here, not this, this. And so now we have something rather concrete. Now, these functions I haven't, because I've only given one instance, they're not defined yet, but we do know that there are has-client instances for them in theory. So, if these did something, we'd end up with, we could reduce this further to just something of type x prime, y prime. And we'll continue going along. And I'll show you the reductions as we go along. I think it's going to help. So let's do another instance. So what we're going to say is we're going to say capturable A and has client B. Okay, now we don't have a type class capturable, so let's make it capturable A. Now I'm not going to give it a body because we'll get onto it later. Very soon, in fact. So this is going to be has client AB. So let's have a look at this. So first of all, we need to get that type sorted, our client type. So remember, what we're doing is we're generating, if you like, a client function. So capturable, that's going to be when we see something. That's going to be when we see one of these. Okay, so we'll say that if A is capturable. I've made a mistake already, so I need here capture A going into B. Okay, where A is capturable. That's what we're saying, and I think I need to do the same here. I apologize. So we want to generate some kind of client function. So if we're capturing an integer, we want to be able to input an integer. So we need a function that takes an integer as input. So our type actually becomes this. And you'll see where this is going, I hope. Client underscore equals, and then here we're going to want client. This is our Now we need to think about what we're going to do with this data here. So this is normally when we change things. So what I'm going to do actually, what I'm going to do is I'm going to change this type ever so slightly. So what I'm going to do is I'm going to give it a list of strings, and this is the strings that we're going to send off. So this is doesn't really matter up until here. So what we're going to say, that's the request we're going to make. We're going to construct this request and then send it off at the end. So what we're going to say is this is equal to client proxy at B, and then we're going to say we need to turn A into a string. So to message, we'll call it A. No, not like that. To message A onto X. Okay, and now we know that inside our class capturable, we need a to MSG, which is A to string. Cool. Nice. So let's save that. Oh, look, there's some errors. Illegal instance. all instances must be, aha, so now we need another type class, not type class, language extension. We're getting a long list up here. And variable not in scope, a, to message, it's not a that I'm after. So, this type is wrong, isn't it? So what we've done here is we have a function a to client, okay? So we look at the class, we have proxy, our list of strings, proxy, list of strings, to a to client. So we actually have an extra argument in this one, so I'm just going to call it z. So z is what we've captured. Perfect. So let's do another one of those reductions to try and see what's going on. So if we call client, and then we give it proxy API and an empty string where our API is going to be capture int to, we'll just call it a generic x for now, or space capture, no, we won't just go y here. So that is our API type here. So what happens here is we have, this is a reduction. So each line I'm going to do a reduction of proxy of type capture int to x or y. Okay, of the empty list, which is going to be the same as client. And so this is the first thing we're going to deal with. It binds the weakest. So those are bound together. That is bound to nothing. So that is our next operator to deal with. So that is going to equal to proxy capture int to x, it's a capital X, I apologize. Or client at proxy at y. That further reduces to I've forgotten the empty lists. And that further reduces to something a little bit complicated, which is kind of like a to client proxy at x of a or client proxy at y of nothing. So if you look carefully, what's happening, we're slowly constructing functions. And that's quite incredible. That's quite incredible. If we had more than one capture, we'd end up with sort of this function list coming along. And that's perfect. That's exactly what we want, because we want to generate this client function out of nothing. Or at least out of the type. So yeah, the next thing to do is probably to add another one of these. Yeah, so I showed you in Servant that sometimes we specify a segment of a URL just with a string on the type level. So, for example, type API equals users. Let's add that in, because I quite like that. I think that's great. So how we're going to do that is we're going to have known symbol S. A string is a known symbol. It's a bit strange. And then has client B. And we're going to say has client S to B, where type client, so this one's nice and easy, of S of type symbol to B just equals client B. We ignore them when we actually go and define our functions. We don't have functions that take in a string. Yeah. And then client, we just remove them. We ignore them when we're actually defining our functions. Let me stick this for good measure in more brackets. Good. And our client function, we ignore that. We have that. And it is going to equal so client at, and we have oh, so this is a fun one actually. Client proxy at B. Now we're going to have at the front of our list, we're going to have S colon X. Okay, where am I going to get S from? I'm not going to call it S because that's confusing. I've called the type S. We're going to call it S prime. Where symb equals symbol val of proxy. I'm going to call it sim actually. Proxy at S. So what's happening here is symbol val takes a symbol, which is a type level string, in the form of one of these types, proxy types, and returns us the string. So quite a lot is going on here. First of all, we have to use scoped type variables because that allows this function to access at S. Okay, this function wouldn't know what S is because S we've got up here. It's not even in the client type at all. We completely removed it from the client type. So S allows us to get any type variable that's in scope here. So that's quite useful. We're of course using type applications. We're using the proxy magic and symbol val. So we do need to import some stuff for this to work. I'm not quite sure what, but I think we will get away with just ghc.typelits, type literals. What have I done? Of course, none of this is valid Haskell because I've just... Let's get rid of it. So that's better. No, it's not. I forgot to add this to my... Oh. Much better. Okay, that's more like it. So it cannot be used here. Perhaps you intended to use data kinds. Yes. So there's another type data kinds. So let's fix it. Nope, not yet. Let's do this. Yes. Okay. So data kinds. Data kinds. Oh God, how am I going to explain that one? Data kinds is when we allow something on the type, no, the sort of the value level to be used in the type level. So I've used this at work a bit. So often I tag types. So I might have data tag, not YAG, tag equals A or B. And then with data kinds enabled, I can define types like, I don't know, expression A. And that, that this is a type, so like eval would often equal, I'll give you a proper example. So this is genuinely some code from work. So mode E or U. And this is a simple type that I use at work. E stands for exciting, U stands for unexciting. So we have a data type, file type at work, which can contain macros. And we have a main program in C++, and we have this program in Haskell that receives these configuration files, evaluates them, verifies them, and kind of compiles them, and sends them off to the C++ component. And the reason that that's done in the Haskell is because it's much better for writing compilers, it's much better for doing validation, it's much safer language. So it means we can really shield the C++ code. We can really have it in this really sort of perfect input and output environment. And in the Haskell, it receives these config files which can have these scriptable macros, and the C++ code has no idea what they mean. And so we have to guarantee that all of these have been removed by the time we send it off to the C++ code. So we have this sort of expression type. We have gats, which I covered last video. So the expression type, I think it's like that. So we're using polykines here. We're giving a type to our type, and we're using gats. So we're saying each one has this mode. So it's going to be, either an E or a U. And that's the data kinds as well, because instead of using these constructors on the value level, we're lifting that so that that is a kind now, and these are types. Very nice. And then I say something like, a value is of type, I don't know, val to expression, anything, say. But then I say this magic macro of doom. Macro is of type, some ridiculous data type, mad data type. E, it's too exciting for our just be mad data type 2 expression E. And, maybe there's some recursion here. So what this guarantees is that everything that contains a macro has this tag E. And it doesn't necessarily guarantee that things without macros don't. Okay? But then we have this evaluation function, which sort of expands all those macros out. And that is of type expression A to expression U. And then the type checker can guarantee that none of these E-tagged things can make it into the final output of that function. So we know for sure, and we get compile errors if we make a mistake, that every single part of the configuration file has been touched and checked to make sure that it doesn't have anything that the C++ won't understand. So that's a really good, simple application of data kinds. I don't think I'm legally allowed to show you that code because it's quite fun and interesting. Why we needed it to use these type level strings, I actually don't know. But there you go. Apparently we need them. And so we get this symbol out and we stick it in the list of things that we're going to fire off to our server. We're going to turn this list into a nicely packed binary message to send over TCP. But I think that's it for this tutorial. Next tutorial, we'll look at writing the server code and maybe, if we have time, the capturable instances, and then we'll just demo it. We'll just use it to do some remote procedure calls. This might seem really alien, and it might seem like we're miles away from anything useful, but we are actually really close to something that's very useful. It's quite incredible. Actually, just before we go, I said I'd do an expansion. Here. Let me just correct this expansion for Okay, imagine we have that. We change this to that. This is still oh, it's a string. That and then on the final line, we do as it says. We basically, it becomes this again, but we have test in our list of things that we'd send off with that request. I didn't put the brackets in here, but it might be more helpful to know that this is what we have, just in case you weren't keeping up with the operator precedence. Why would you? Okay, that is actually it for this tutorial. I'll see you next week, where we'll continue making our remote procedure call type level library thing. And after that, we'll deal with servant, making sort of really useful web applications in Haskell. Okay, see you next week. Bye.